All right, good morning, everyone. Come on in if you're still looking for a seat. We've got a few up here and this table over here. These tables have some empty spots. Come on in. I want to welcome all of you to the second annual Mass Spec Summer School that we've put on, and really delighted to have you all here. So before we get started this morning, I want to just sort of go over today's program a little bit and tell you a little bit about what you're going to learn today and introduce a few of the concepts. Start out though, if you flip through your program, you'll see that we have a Twitter hashtag, and we encourage you to send tweets. I don't have an account myself, but we have one set up. And we're going to be monitoring that, and every evening we're going to give one of you an award for the best tweet of the day. So you can strive to achieve that. I also forgot to say last night I wanted to thank our refreshment sponsor, Promega. They kindly provided the beverages and some of the food for last night's mixer, so thank you, Promega, and if you are in the market for reagents, they're the place to go. Okay, so to the summer school. So our hope for you this week is to sort of learn about how mass spectrometers work. This laser pointer is kind of light. How mass spectrometers work, and is it up there? Oh, there it is. It's very faint. So today we're going to start with this mass analyzers, and we're going to start today's lecture. Our first lecture will be about mass analyzers, and we're going to try to teach you the basics of how they work, and then that's going to be immediately followed with some hands-on demonstrations that we've been setting up, and they're intermixed with the poster. So after that first lecture, we'll go out and please check out all the different stations, and we'll try to reinforce some of these concepts. And then after that, we're going to have a lecture on ionization, so you can learn to measure the mass of something. We have to have a charge on it. How do we go about that process? And after that, we're going to take a lunch break. It's going to all be served out there, and I think you eat in here. And then we will have a lecture on tandem mass spectrometry, followed by another lecture on separation. You know what? This is like, what am I doing? I could just hit this button. Okay, so Mike Westphall is going to do the lecture on mass analyzers. That's his photograph. And then we have Evan Williams for ionization. And then I'm going to be doing tandem mass spec. And then you're going to hear about separations from Evgenia. And so that'll take us up until early afternoon. And then we've fit in two professional development topics that I think you'll enjoy. So if you recall, when you signed up for the class, you selected one or the other. We're not going to bind you to that, so if you can't remember, just pick what you think is most interesting. Just introduce those. We have Charlie Trevor, who's a business professor, and he's got this fun lecture on negotiations. If you're going to be looking for a job soon, the whole thing ends with a job salary negotiation, so I'll get you ready for that. And then we have Mike Falk from our Patent Foundation, and he at the same time will give a lecture on intellectual property, and he covers the case of Stanford versus Roche. It's a very famous case in intellectual property law, and if you want to do that one, there was a reading you all should have received. If you don't remember getting it or you don't remember it, if I have some volunteers, we've got handouts for the case, so you could just brush up over lunchtime. So if you want them, raise your hand right now, and I'll pass it out, and you'll have them ready to go. You all raise your hand. I don't have that many, because half of you are going to see negotiations. Okay. So raise your hand if you want a cop out of the case, a handout of the case, and then you can brush up over lunch. And if you decide later you want to get one, we'll keep the handouts out on the front desk. All right, so think about which one you want to do. And then we're going to end our afternoon with a poster session, and we're going to learn about each other's science. And we're going to have some hors d'oeuvres and beverages. Tonight's cocktails and hors d'oeuvres are going to be sponsored by Thermo Fisher Scientific, so we want to thank them for that. And that's introduction to today's program. Any questions before we get started? All right, save all your questions for Mr. Westphall, Dr. Westphall. Yeah.
You just turn it on.
Okay. All right, everybody. We figured we'd start the day with everybody's favorite topic, physics. But what I really hope to do, not make physicists out of you, but try to develop an intuitive feeling for what's actually happening inside a mass spectrometer, so you can kind of make, or at least understand what it is that's happening when you change a voltage or change something on the control panel. And it's kind of, what do I want to say? The mass analyzers, without them, we'd be kind of stuck. So, let me see here once. Before I get into that, I know many of you made it down to our gathering last night, and I heard people commenting on how peaceful it is down by the lakefront. And I just put this up here. This was a photograph taken by Jean, a postdoc in our lab, just this past Friday, which kind of shows the calming effect of the lake. So if you didn't see it in the national news, basically what happened is there were several massive transformer explosions all at the same time. And you can kind of see one going on there in the background. It was enough to basically put 13,000 people in this area without power. They closed the government buildings. They activated the National Guard. And even with all that said, you can see there's not a single person in this photograph looking at it. If the end of the world's approaching, I say just go down to the lakefront. You'll be very calm. It'll all be good. But nonetheless, I do recommend checking it out. All right, and so here we go. Can anybody tell me what that is? Yep, so that's the problem with mass spec. You could be here all week. I'll show you this slide, and there's still no way you can tell what that is given the information that you have here, unless you happen to see it at one point in your life. So before we get into mass analyzers, I just want to give a very, at least what I think is a somewhat simplistic analogy of what you need to do with mass spectrometry to make it useful. And so we're going to start with a watermelon fruit salad. I know this is kind of a strange analogy, but it's the only thing I could come up with. It turns out that we want to make one of these. And the only information we're going to have available to us basically are masses. All right? And so we have to have some prior information. And that is basically we have to know how much our individual components weigh. And so a green grape on average weighs 2 times 10 to the 24 AMU, atomic mass units. That's important because we're going to switch to that eventually. But we'll stick with grams for now. So you can see we have grapes, cherries, blueberries, and watermelon balls. And so we decide we're going to buy our fruit from a very hoity-toity company that sends them in crates. One piece of fruit at a time. We can't see what it is. So what we can do here is weigh it. So now if you're paying attention to the previous slide, what is this? Oh, you guys are going to have to pay better attention. Okay. All right. So it's 1.5 grams. It's the lightest thing. It's our blueberry. Exactly. All right. And so if we measure these crate after crate, eventually we're going to get a small distribution based on our ability to weigh things, whatever it may be. And we kind of start forming a simple mass spectra. We now have a blueberry. So I'm just really confuse you here. All right, so we continue this process and we end up with another mass. This is now our heaviest one. So we now know we've added. Sweet, very good, very good. All right, so here's where the conundrum of mass spec comes in. We continue to weigh things, and here's where our problem is, right? We now have something at 3.5 grams. We had 2 pieces of fruit that weighed that. And so all of a sudden we can no longer make a decision based on mass alone as to what this is. And so fortunately, we kind of plug along, and we realize that these two pieces of fruit, which weigh the same, have unique identifiers, and that's basically their seeds. Their seeds are of different size. And so in order for this to be of use to us, we need something, this little doodad down here that I found online, had no idea it existed. But what it does is it removes seeds and pits from cherries and grapes without destroying the grapes or the cherry, and it just spits out the seeds. And so now what we're going to say is this little device is going to be our MS2. This is what we're going to call fragmentation dissociation of the thing that we're interested in. And so this does it in a very predictable manner, and it's going to spit out 2 crates. We're going to weigh those, and this is what we have. So now we basically, every time we come to a 3.5, we know we want to select that. We want to fragment it by putting it into our little magic defragmenter. Oops, let me find one of these, which actually kind of works. And so then for each one 3.5 gram thing that goes in, 2 come out. And so what we now realize is that the cherry had the heavier seed. So it's going to be here, and it's going to have lost more weight than the grape because it's total mass made up by the seed. And so we know this peak combination of these 2 is a cherry. So if you select your 3.5, fragment it, you get these 2 peaks, you have a cherry. You have these 2 peaks, you have a grape. And so the bottom line is you can then eventually determine how many of each thing you have for your fruit salad. So as simple as this may seem, I have a horrible saying. I used to say the only people who like mass spectrometry are those who've never used it. And I think that's because everyone's under the impression that they're just going to give you your cells, your tissue sample, your whatever it is. You're going to put it in and get this magical answer out. And that's the problem with mass spectrometry. You'll always get an answer, okay? The problem is trying to determine if it's the correct answer or if it has any meaning at all. Because the one thing it can do is generate peaks, and it generates more peaks than you could possibly imagine. And so keep that in mind. If you don't think of anything else this week, the 2 things that you need is you need to have a very good guess or understanding of your initial population that you're putting into the mass spectrometer. So you have to have a good expectation for what it is that you're going to see. And then you need to have a very good means of fragmenting it in a predictable manner. So if we would have taken a hammer to our grapes and our cherry and just made mush out of them, we would have had peaks everywhere and we couldn't tell them apart. And so people that work on technology development for mass spec, we spend a lot of time trying to figure out how to fragment certain populations of ions in a predictable manner. And so like Professor Kuhn is known for ETD. That's one method of doing it. There's HCD, CAD, ion fragmentation, photofragmentation, you can go on and on. But basically, those are the 2 components that you need. You kind of have to understand how they work if you're going to have any inclination or any hope of trying to interpret what you've done. And so this thing that I've shown is actually myoglobin. And the reason that I knew that in this case was the only thing that was put into the mass spec. And since we can't actually work, oh, really? Thank you very much. Oh, look at that. All right. All right. And so as you can see, this is just one thing into the mass spectrometer. This is the MS1. We can't work with things that we put on the scale. We have to get them into the gas phase and ionized. And this process can actually take the simplest of things and make it very complicated. And so, as you can tell, this is why, now hopefully, the first thing we have to do is get it from the solution or your tissue or whatever it is, ionized, meaning you want to get these molecules into the gas phase. And Evan's going to be talking about that, as you heard. You can also see that if I didn't know that this is what I put into the mass spectrometer, if I had an idea that it was one of two proteins, for example, we would then have to do some type of fragmentation on this, break it apart in a predictable manner so that its little constituent components would show. And Josh Kuhn is going to talk about that. And then as you can see, just putting one thing in makes it very complicated right from the start. And so what you want to do is minimize the number of things you put into the mass spectrometer at one time. And so that's where the upfront separations comes from. And that's what Evgeny will talk about. All right, so now we're going to get into the physics of things. Once again, interrupt me at any time. The goal is to not learn math. We'll try to keep the math to a minimum. And what we're really going to do is just try to get an intuitive feeling for what's going on inside a mass spectrometer. All right, so as I said, we can only work with charged particles for everything that we do. All right, so all that means is that at some point, we've ended up with an imbalance between electrons and protons. And that's what the ionization process does. And so basically, if we have a positive ion, we just have more protons than electrons. So this is good. So this is the number one requirement is it has to be able to be charged. So you have to get it from whatever you're starting with, the final result before it really goes into the mass spectrometer is it has to be charged. All right, so now here's where we're going to start physics. And these are going to be the only two things that I'm really going to try to have you understand, okay? And so if you think of it simply as on the very basics of things of like charge don't like one another. So positive charges are going to want to push each other apart. A positive and a negative charge are going to want to pull themselves together. And so there was this gentleman by the name of Lorentz who finally, after all sorts of studies, came up with the forces experienced by a charged particle. So you have a charged particle in space, and you expose it to electric fields and magnetic fields. This is what it experiences. So we'll get back to this in just a second. And so then from Newton, way back in the day, force is also equal to mass times acceleration. And so in the simplest of case, if two particles are experiencing the same force, but one is heavier than the other, this equation has to balance out. So this means if the mass of the one, since it's heavier, means its acceleration has to be less. And for the lighter particle, since this value goes down, this value goes up. So what that means then is as they're exposed to the same force, the light particles are going to be accelerated more, and they're going to end up going faster than the heavy particles. And it also means that it's going to be easier to turn a light particle than a heavy particle. And so these are kind of really just the basic things that we need to worry about. So you kind of think of it as if you have an ocean liner or an aircraft carrier, as the saying goes, it takes forever to turn it. If you have like a little boat, you can zip it right around. So now we'll go back to the Lorentz force. So we can have, this is everything you need to make a mass spectrometer. This is the forces due to the electric fields. All right. And the one thing to remember here, not that this matters for us, but just keep in mind, is that these are, the bold things are vectors, meaning that there's direction associated with them. All right. So it's not just a magnitude, but it's also a direction. And if we look at the magnetic portion of this, this is kind of interesting. So what it kind of shows is the cross product here. That's what this stands for. It's not a multiplication, but a cross product. What this really means is that the magnetic field's only going to act perpendicular to the direction that the particle is moving. All right? And the other thing that you'll notice is it's dependent on the velocity of the particle. And this is kind of the important one. So let's say we have a magnetic field, we have a charged particle, and it's just sitting there. So velocity is 0. That means there's nothing we can do to get it to move, right? But once this particle starts moving, If we do something else, give it a little shove, we'll see here in a minute that since it has some velocity and has a force now acting to it perpendicular, it's going to turn. So the only thing a magnetic field can really do to a charged particle is turn it. It won't increase or decrease its velocity and magnitude, just its direction. And so the way I look at this is you can never have a mass spectrometer with just a magnetic field. So this then leaves us with the electric field. And as we'll see, that's why all mass spectrometers have electric doodads in them. So for one, even if you have a magnetic sector, an FTICR, whatever it is, you can't get away without this component if you want a mass spectrometer. Basically, you have to do something to impart energy, get these particles moving, and introduce them into the magnetic field. And so with that said, I am not going to cover a whole lot on either of those instruments. Just the basic concept is this. So there's a thing called the right-hand rule, not that that matters. And the way that you represent magnetic fields, directions, are the X's you kind of think as the back, the feathers of an arrow. So that means the magnetic field's going into the board. If it was a dot, it's coming out. But the important part here is you can see if you have a positive and a negative charge molecule, and they're coming this direction, so they have a velocity, they hit the magnetic field, they're going to turn. They're going to turn opposite directions. Now, the only thing to remember here is if there's a term in nuclear physics, which I find very useful for this type of thing, it's called magnetic rigidity. And so it kind of makes sense. It's kind of like how rigid a particle is when it encounters a magnetic field. So something which is heavy and is moving really fast, for the most part, or fast enough, is going to barely be turned by this magnetic field. So it's going to seem really rigid. Whereas a lighter particle is going to be more likely to zip off one direction or the other, and it's less rigid. And so its magnetic rigidity is less. And so if it happens to be a confined magnetic field, it comes in, it turns, it leaves, and keeps going out its merry direction. Didn't speed up, didn't slow down, just changed direction. Now, if you keep it completely enclosed in a magnetic field, then it just continues to turn. Doesn't speed up, it doesn't slow down, it's just in there going round and round and round and round. And that's basically how FTICR instruments work. You have a charged particle in a magnetic field, and it's just going around and round and round in circles until it runs into enough things to finally stop. And what you look at then is simply this frequency that this thing is going around in the circle. And that will, in the end, define what its mass is. And there's almost analogies to all of this in the electric forces. So we'll see that. And this is all I'm going to cover on magnetic fields for this. Now, if you guys want to discuss more with me later or anytime, I'm here all week, so that's perfectly good. We do have out there a little demo. I think there's two tables there, which I think is kind of fun to play with, but it'll give you a feeling for what magnetic rigidity is. And so what your goal is, you'll be given a selection of steel balls, one, of course, which isn't magnetic at all. And then what you want to do is you want to set this up so that you separate all the balls based on their mass. All right, and so if we think about what I just said, this kind of makes sense, right? So our biggest one, so we're just using a magnet to create a force, even though this isn't charged, there's still a magnetic force down here. This one's going to have the highest magnetic rigidity. It's going to be the hardest to turn. So if we impart the same amount of energy, or we give these guys all the same velocity, I should say, this one's going to take much longer to turn than the lightest one. So keep that in mind as you try to set this up. Conceptually, it seems simple. Making it work is kind of frustrating, but which is kind of like mass spec in general. All right, so we will now switch to electric field forces. All right, and so now this time, since we just have the amount of the force that they experience is going to be their charge times the electric field. And the electric field is in terms of volts per centimeter, think of it that way. And so if we have these two little parallel plates here, kind of like a capacitor, we always draw our electric fields going from positive to negative. And this equal spacing of them shows that there's no gradient. And what that means then is that the electric field's uniform within this region. So if we had just particles sitting here, they're going to go from 0 and take off and be accelerated. And so if they're positive, they're going to want to go towards the negative, and if they're negative, they want to go towards the positive. Now, if we could also do an equivalent where we send them in from the side with a bit of energy or velocity. So now, since the field that's perpendicular to them is not going to have any effect on whatever component that it has velocity going this direction, they're not going to speed up this way, but they're certainly going to speed up this way or that way. And so the end result then is that they turn. So turning is a useful thing, but it will turn out as you will see. And so this becomes our electric sector instrument, which is the same as our magnetic sector instrument in a way. And so now all we're doing is we're sending in a bunch of particles, same velocity. The bigger one's going to turn slower, has the F equals ma scenario. So it's going to go further before it finally comes down and hits where this black line is, which I'm going to call the detector, right? And so what you could do is you could have your detector, or in the case for a magnetic sector experiment that you're going to have out there, our piece of foam, you can have your detector cover this entire region, or what you can do is, as you, say, turn down the magnitude of this field, then basically this black ball, our charged particle, is going to go even further. They all will, and then eventually this blue one will come into contact with the detector. And so then that way, it's just a very simple way to scan for mass to charge. Does that make sense? Okay, because it's going to keep getting worse if it doesn't make sense at this point. All right, so the first mass spectrometer we can think of just using a simple law is time of flight. So have people used time of flight mass spectrometers before? Okay, perfect. So we're not going to go into great detail on them, but it's very simple. It's just like a good way to explain the thing that we just talked about. So here we go. So here is our plates. So this is going to, we're going to say this is negative, this is positive. This is the thing we were just looking at. Here is our two ions, one's heavier than the other, all right? So if they pass through this region and they both experience the same force, right? Because they traverse the same amount of electric field. So that means the lighter one is going to have more acceleration, meaning it's going to be at a higher velocity at this point. So now what we do is we leave this region into what we call a field-free region. So there's no voltages here. It's just vacuum, nothing else. So basically, at this point, the particle which is moving the fastest is going to obviously traverse this region the fastest. And the thing which is the heaviest is going to traverse it the slowest. And so what you do then is you basically have a detector down here, and you're just recording the signal as a function of time. And based on the time when things hit it, you convert that and you get yourself a nice little mass spectra. So once again, this is just to give you an intuitive feeling. That's how time of flight works conceptually. Making it work in reality becomes much more difficult. But nonetheless, these are still the basic principle behind what's happening with time of flight mass spectrometry. All right, and so these are fairly common instruments, and so you will certainly be exposed to them. But just remember, all that's happening in a time of flight instrument is this. It's that simple, nothing more. All right, so I want to move on to trapping instruments. And so this is kind of interesting. I've always kind of liked this, Earnshaw's theorem. So what this means is if we have a positive particle sitting right here and we want to hold it in space, basically that means we would need to have our electric field going this way, pushing it in from all sides equally at all times. All right, but there's a problem with that. In order for that to happen, we would have to have a negative charge sitting here and not a positive charge. So the take-home message of all this diagram, which I realize if you think about it long and hard, it may dawn on you, is that you can't trap an ion with static electric fields. Okay? And so there's like no way to hold a particle in space using DC fields. You have to keep something moving. You're either going to move your ion or you're going to change the electric fields. And so basically what you kind of think of it as, periodically you just want to swap out this positive charge, which is sitting here, with something which is negative, and then swap this back in. And so as we'll see, one of the easiest ways to do this is using AC voltages as opposed to DC voltages for trapping purposes. All right, so now we're going to go back to our simple analogy of our parallel plates. But this time, we are going to have an AC field on them, right? And so all I mean by that is simply, I guess it's like a squiggler. It's this a sine wave, we'll say plus and minus, that's changing as a function of time, as opposed to just a constant voltage. We'll say this is ground down here. Can anybody actually see that? All right. So here's what's going to happen. If we set our charge right there, it's just stationary, and we turn on the AC field, here's a couple things that are going to happen, I think. I hope. All right. Let me know if this writing on the board just doesn't work. Let's see. Okay, so we have our plates, and so at one point, when this one is positive and this one is negative, we have our particle here. It's going to want to push it down that way, correct? Just like the static field that we saw. So it is then going to move down some point in time. I trip over that. Sorry, trying to make these people able to see. It'll move down here, all right? So now, since we have our AC field going, it is going to, is it impossible to see?
The red is extremely difficult.
Okay, can you see? Okay, we'll go with black. All right, no problem. So then as this field changes, it's going to pull the particle back up this direction, correct? Then it's going to switch and it's going to go back down this direction. And so what's going to happen is, if the magnitude of this field and the frequency of this field matches up nicely with our ion, it is really just going to sit here and go boop, 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 right about the center. It's just going to move up and down, and it's always going to be 180 degrees out of phase with the field. So what that means is just what I showed there. It'll go this direction until the field turns, so it means it's going to be down here. Field changes direction, starts going back up there. That happens. And so then it just kind of sits here and does this for however long you want it to be. All right, so now we got to think about several scenarios, which will come in handy. So one is, if we have this AC field too high, our amplitude too high, what's going to happen? That's right. We're going to basically run into one of these two plates. All right, so that'll be a problem. The second thing is maybe a little bit more difficult to, I don't know if it's, I can draw this. Okay, so here's the point that I want to make. So let's say we have a object sitting here, and so now I'm going to bop it up. So it's electric field, I'm pushing it up. And so if it's big enough, it kind of starts moving slowly, right? And so now what I'm going to do is increase the frequency of my AC field, meaning that I'm going to change how quickly I bop it again. So basically, if it just starts moving this way, and I immediately come up and bop it so it starts going down again, I do that. And as I do this faster and faster and faster, pretty soon, the ion's not going to move at all. Does that make sense? Okay, so basically, even though there's an AC field on it, the frequency is such that It is going way too fast for that ion to respond to. And this will be important as we go on. All right, and so we're going to do another take. And so now we're going to slightly bend our parallel plates. All right, so now what happens is the gradient or the field lines are going to be closer up here, which this means it's going to experience a stronger electric field up here than the field strength down here. So now we can do the same analogy. We apply our AC. It first starts going this direction, but the field's getting stronger as it's going that way. So it then wants to stop. It won't go up as high. It turns around, starts coming down this way. The field's not as strong down here as it is up here. It's no longer symmetric. So that means it's going to go further down. And so what's going to happen then is after several oscillations, we're going to move it down and it's going to collide with this lower plate. Now, does that make any sense at all? Okay, because this becomes a very important concept. So basically what it means is if we go simply from a uniform electric field to one which is not uniform, has some type of gradient, it's changing in space, we can actually push it around with our AC field. But what's kind of cool about that is you can now think that, okay, the way this setup is, it's always going to push it down this way. So we could add a DC component to this and push it back up that way. So we could balance out the AC and the DC field to kind of have it oscillate in a spot. You know, we can kind of, by changing the DC voltage, we could say it's going to oscillate down here, it's going to oscillate up there, it's going to oscillate in the middle. And this is kind of how the majority of ion traps and everything else works, as we're going to see. So what you do then is you go to the extreme and you really bend these plates around. And so this is a quadrupole. And so the math tells us that quadratic fields are going to be very important. But we'll see if we can kind of try to conceptually get that. So now what this means is you can see that these arrows here are getting closer together the further we go from the center. So what that means then is that these forces are getting stronger as we move away from the center. And exactly at the center, the force turns out to be zero, if you could just get it to match up nicely. So that is kind of every time the ions move off axes, it's going to want to, it's going to experience a stronger force and it's going to oscillate back that way. So it's going to kind of want to oscillate around this central region, which is fine for trapping. All right, and so now we're going to look at, well, what if we want to go beyond trapping lots of things? And I've already alluded to it, that it's this combination of either our amplitude of the AC, frequency, or our DC, how much DC we put on it. And so the way a mass selection quadrupole is going to work is that on one of these set of rods, in this case our X rods, both the X and the Y rods have an AC component which is identical in frequency and amplitude, but it is out of phase, meaning that when this one is positive, this one is negative. And then when this one becomes positive, this one becomes negative. All right, and then in addition to that, we're going to apply a DC potential to each set of rods, but of a different polarity. And so one set of rods, we're going to have a negative value. The other set of rods, same amplitude, but positive. All right, so we'll look at these one at a time. So now we're going to look at the Y rods first. So what we have then is we have our AC field. And so in something which matches up nicely with this AC field is just going to want to sit there and bebop around. And our little DC field that we put up there, you know, we may be able to center where it's oscillating a little bit. So now the question is, what happens as we increase, I'm going to say in this case, how to put this? Increasing the frequency, which I don't want to say, is going to kind of be the same as changing the mass of the ion, right? So it's like a, let me grab the black one here. Oh, thank you. All right. So basically, given the a certain AC component, and depending on the size of our ion, right? One of these is going to be able to keep up and ride merely along with the AC. And one of these may be so large that it can't see the AC field at all. All right? And so, if that makes sense, it probably doesn't, here's actually what's going to happen. So now we take this ion. So if it's of light enough mass, it can react to the AC field and the DC field. And you might hit this little parameter where it's can kind of be held. If it gets too light, then it's going to strongly react to our AC field. And our AC field is such that the amplitude is going to make it smash into the rods. Once it gets large enough, it can no longer react to the AC field, and now it can just see the DC field in this dimension. And so what it sees is a plus here and a plus here, and it's like, well, I'm not going anywhere. So what this actually kind of acts like in this dimension, to a degree, is a high-pass filter. Meaning that you're going to reach a point where ions of a lesser mass are going to crash out, and ions of a higher mass are going to be okay. All right, and so now we do the same, but we look at the other set of rods, which has the negative potential. Same effect, right? So the thing that happens this time is that once we reach that point where we can no longer see the AC, or the AC has very little effect on it, it's basically going to notice these DC fields. This time they're negative, and what it's going to want to do is suck the ion over, and it's going to collide into the rod. And so in this dimension, we have what's called a low-pass filter. And in the simplest of cases, it's going to let the lighter molecules through, but not the heavier ones. And so then, if we combine it all together, you can see what we end up with is something called a bandpass filter. There's going to be a region, a certain mass, for a given AC, DC conditions, along with your trap conditions, that ions in this mass range are going to be happy to stay in there. All right, so have I lost everybody? Yes?
What happens with ion when you mix the rods?
Oh, so that's a good question. People ask that all the time. All right, so it's kind of like, as we'll see when we get onto orbit traps and things just crash into the rods. And a simple answer is, if you own a mass spectrometer, eventually you have to clean it. How's that for an answer? So ideally, they used to think, what the hope was, or we would advertise this was, if this ion would come in contact with the conductor, it would then be neutralized and then get pumped out of the system. So I'm sure a certain amount of that happens, but you can easily get the front part of your instrument dirty enough that if you use the correct solvent, you can wash it off, mass analyze your solvent, and see which ions happen to stick inside your mass spectrometer. So eventually, as we'll see, they can still be relatively maintenance intensive depending on what you run through them. So they'll need to be cleaned, and detectors, when we get there, need to be replaced, basically. So that's kind of what happens to them. All right, so this was in, of course, just our 2 dimensions here. So this, we can't just set an ion right in the middle, would be kind of nice. And so then this becomes yet another mass analyzer. So we've now had time of flight, and this is what's known as a quadrupole mass filter. I couldn't find a picture where somebody actually drew it as quadrupoles, so they just drew them as cylinders. Cylinders work Not that we need to worry about that. What you have to do is you have to move them further away from one another. And then by the time you get to the point where you want to be, the fields are kind of the right shape. So now what happens is you start here and you send all your ions through this direction. And there's going to be a subset of them where the DC and the ACs, to their liking, they're going to pass through. And there's going to be another set which are going to dirty things up, basically. They will crash into the rods. And so this is all well and good conceptually, but we need to kind of think about, to get a better handle on how these things really work. We're not going to go deep into the math of anything here, but basically what engineers and physics people like to do is model everything mathematically. And we can never really do things too precisely, but we come up with good close approximations. And so what you do then is you basically define your potentials, and there's your field. This we won't need to worry about. This is just another thing in physics, which kind of states our boundary conditions. But what you can do is use all these things, shove all this back into the Lorentz equation, set that equals to mass times acceleration, kind of work out some of the math. And the problem is, as with most things in physics, you can never actually solve these things. You can approximate them, but you can't solve them analytically. And so these, of course, has the name, I say Matthew. I don't know if that's a correct pronunciation. I've always called it that. So one thing you'll learn if you ever took physics in college is that the entire universe oscillates. All right. There is not a thing in physics which is not described by what I call a simple harmonic oscillator. Basically things doing this all day long. And so what this person was interested in was, if you have a drum head, which is not round but elliptical, and you hit it, what type of standing wave sets up in the drum head? And that's this equation. And it turned out that when you look at trying to model a quadrupole field for doing mass spectrometry, everything falls into that equation. So we basically end up using his solutions to solve how our ions are going through a mass filter or any type of quadrupole ion trap. All right, and so the important part of all this is, kind of, sort of, in order to, and I'm just including these because you see them all the time in the literature. And so what he did was he did these variable substitutions in order to solve or come up with the best approximation of his equation. And so when you look at it in our world of mass spectrometry, these variable substitutions then, this one and this one, are made up of m over z of our ion, the frequency of our AC component. This is basically the size, the spacing of our quadrupole rods. And then this is the DC field, and this is the AC field. All right? And so even though he crammed it all the way down into these two variables, these also become the two variables that we like to look at. And so what this U means, it could be any dimension. So remember, everything's in a vector, so we could say this was X, or this is Y, or this is R, or this is Z, whatever way you happen to be looking. It allows you to look at it one dimension at a time. Okay? And so then, what this does then is he plots, or you can plot, solutions to where the equation is solvable. And what we do then is anything which is in this region is going to be considered to be a stable trajectory, meaning that it's going to be happy inside that AC field in this one dimension, the AC-DC combination. So this is the values of Q along this axis and A, or in other words, if we keep everything the same, the values of our DC amplitude and our RF amplitude, where that particular M over Z ion will be stable within a quadrupole field. Okay? So then what you do is you start adding in your other dimensions, and this is something that you see a lot of times. Okay? And so now what this does is this is just looking further out, and so there are many regions where you could have stable trajectories, okay? But in order to get to some of these, you can kind of see that our value of A and our value, well, particular, I guess, and our value of Q's often has to be increased. So it means our voltages get larger. So what you do in reality then is you work in the smallest region right down here, okay? Because that's like simplest to implement. And you can go through the literature and you'll find people done studies in all these various different regions looking for some other type of behavior. But what happens then, if we blow up this region here, this is what it looks like. But since this for us represents our DC field, we don't want to change polarity of it, so we're just, because we have a plus and a minus, so we just go one dimension. In the end, this little region right here is our stability region, which we kind of use to help define which ions are going to go through. And so another way to look at that is, so if we take this A and this Q, and for a given M over Z, we fix the M over Z, we fix our frequency, we fix our trap dimensions, and we replot it, you can kind of see that, okay, we have that general shape, correct? And so these, for this particular M over Z of 219, this is where it's happy. Any of these RF DC voltage combinations are going to keep it as happy as a clam. It's going to pass through. And you can see for a lighter ion, it's smaller, but this is its region of happiness. And then what you will notice is that you can draw lines. Well, hopefully we all knew that. But this is going to pick up the term a scan line for quadrupole mass filters. So when we scan out ions as a function of M over Z, what we're actually doing is we take a fixed ratio of the DC amplitude and RF amplitude, all right? And all we do is we keep that ratio the same, but increase both of them. And so that slope of the line defines our ratio. And then you can see by adjusting our ratio, we can adjust the slope. And if we look at the dotted line here, this would be our M over Z that would go through. And you can see the further down we are, the less our slope is, the wider these are. And as we increase our slope, it begins to narrow up. And so if we pick the appropriate ratio, then we get way up on this little corner. And that gives us much better resolution, okay? Or we can do the complete opposite and get rid of the DC, drop this down, have it be flat. And what that means then is most any ion is going to go through. So it's going to allow it to pass, but you're not going to be able to do any type of mass filtering with it. That's important because everything inside a mass spectrometer, for the most part, which gets your ions from mass analyzer 1 to mass analyzer 2, is just more or less a mass filter with no DC component on it. So it's just what we call an ion guide. So it could be a set of, you don't have to get as fancy, it could be a set of 4 round rods, it could be whatever it may be, but there's just an RF component on it. And what that does then is as the ions enter it, they stay trapped and you kind of make their way merrily along to the next part of the mass spectrometer. All right, so as we look at the mass filter, and this is going to be used in a lot of mass spectrometers, what would be the simplest way to make a trap, you would say? So now you've been able to, you have this thing where you always have ions, kind of a beam type approach where you're selecting as they go through, and now you may want to trap something. And so, interestingly enough, the easiest way to do that is just put a couple of plates at the end of your mass filter. Okay? So, conceptually, here's what's happening. 2 things have to take place. What you're actually doing then is you kind of have think of it as a DC potential on both of these plates. And if that potential wasn't there, we kind of have our normal, our ions go wiggly wiggly through. And now we want to stop them. And so what we have to do is we have to change the potential either, well, the way this is drawn, we're lowering the offset of these rods, which is the same as increasing the offset of these rods. So the way to think of this is that if we were just to put, we're going to look at just the positive one. If we just put a high positive voltage on here, positive ions would come in, they'd wiggle, 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 they would see that, and then they'd want to turn around. All right? So they would then turn around, and they would actually come right back out because there's nothing to stop them. And so then you would say, well, why not just at some point raise that? So they could come in, sees this, turns around. By the time it gets back here, you've increased the voltage on this lens so that it can't come out. All right, so yes, you could trap something that way. The only real problem with that is that you now have a time-dependent trapping, which isn't the same for all ions. So the ones that get trapped in there are going to depend on a lot of the initial conditions of its ion, not only its mass and its charge, but the velocity it was going, all these types of things. And so what we do then is, in addition to having this potential offset, the way to think of this is that our positive ion is a little ball. It's going to roll in, it's going to go down. Whee! It picked up all sorts of speed. In fact, it picked up enough speed to go back out this side. So now what we need to do is we need to introduce something that's going to take away some of that speed or oomph. And so what we do then is we introduce helium. Just a small amount of neutral helium molecules. And so the full purpose of that is they come rolling in, they start having collisions with the helium background, and it slows them down. So that by the time they get over here, they've lost enough energy that they can't make it back up over this hump. They turn around, lose a bit more. And so now they stay trapped and just kind of meander in here. And so that is a linear ion trap. That make sense? Okay, and so, of course, when we go into ion traps, they're kind of all the same, but look different. And it just depends how you want to define your dimensions. So this is called a three-dimensional ion trap. So this is kind of like where you've taken a single quadrupole rod and you've bent it around in a complete circle. And then you put parabolic lenses on it. And so now all the equations still hold, but instead of x, y, you have your coordinate system, so you have an r and a z. So conceptually, nothing changes. They both operate in the same exact way. The only difference is that the space available to hold ions is much larger over here, as you can see, than it is over here. And so one of the problems that you run into is you're always trapping, for the most part, molecules of the same charge. They don't like one another. And there's only a certain number that you can confine within a region before bad things start to happen. And so if they're able to spread out along an axis, you can get many more of them in there. And so to conceptualize the trapping a bit more, I don't know if this is going to help or not, but when you go outside later, this is what, so now if I took that 3D trap, okay, and just took a slice through it, and I now plot the potentials, okay? And so this is the end caps, and this is the bent rod going around here. So you can see the way this is, these potentials are, it's kind of like a hump this way, and it's going down this way here. And so at the next moment in time, as our AC begins to change, at one point, this will all be completely flat. And then the next point in time, these will be high and these will be low. Okay, can you kind of picture that? So now, think of it as setting a ball right here. So you're going to set a ball here, and it's going to start to roll down this way. But then, at a certain point in time, this flattens out and goes high. So now it wants to roll back this way. And so if you were changing these at the appropriate frequency, you should be able to trap a ball in here. And so we have an apparatus out there. You'll go out there and you'll see it. They have exactly this shape. Kind of like how tall they are represents the amplitude of the electric field. But instead of having them flap up and down, they actually rotate. So we kind of think of it that way. So as a function of time then, what's high in this direction will be high in this direction and vice versa. And so that can give you kind of a good feel. You can adjust the frequencies, do other things, kind of get a feel for what it takes to actually try to keep a ball in the center of this thing. And then there's one other apparatus you can look at to try to get a feel for what's going on. And this is, we set up a system for trapping at atmospheric pressure, basically. All right, and so the simplest way to make a quadratic field is actually to have a ring, just like a ring, inside a grounded box. All right, so if we look at this face on, it looks like this. Look at it from the side. You apply a potential to it. The way the fields go forms a nice little quadratic field. And so then what we do is we use some spores, which we can statically charge. You can put them in this thing, and then you can start playing around with the AC and DC fields and see what happens. And so like you can see in this image right here, you can actually see hints of that lovely quadratic field. And so this thing's kind of a lot of fun to play with. Evgenia will be standing there. And the hope is with these two demos, you can try to get a feel for trapping. All right, so now that we've trapped things, basically we need to worry about getting them out and appropriately in a mass selective manner. And we're going to do this a bit differently than we did with the mass filter. So the mass filter was basically called mass instability. So you're changing the AC and DC fields to the point where it's no longer stable as a function of m over z to select what you want. So in order to do two things, one, mass selectively read out a trapping device, or to mass selectively fragment something, we kind of have to look at the motion of the particles in the trap. All right, and so what we see here is, so this is the 3D trap. And so they're kind of making this cute little pattern going around, around, around. And this is the linear ion trap, and they're kind of going back and forth. But what's interesting, you can see it best here, is that along with this macro motion, each dimension has its own little subset of frequencies, which we're going to call the secular frequency. And that's going to depend on the geometry of the trap, the type of thing that you're using, okay? And so you can also see it in the 3D trap. So you kind of, this looks like it's making this figure, but it's also making a little sine wave as it does it, and it's also kind of doing it in multiple directions. So if we look at a model of linear ion trap, which we saw earlier, we have black and blue, which may be hard to see here, but what that represents is the two dimensions, x and y, okay? And so the ions are just going to continuously follow these paths. And you can see in one dimension, it's a little out of phase of the other direction, meaning that the motion's identical, but it's just delayed a little bit in time. But the interesting part is these little tidbits right here, all right? And so what this points out then is that if you were to do a Fourier transform of these things, basically what you want to do now is find out which frequencies are present. You're going to have this massive, this is the main frequency, the macro motion. But then you also have these two little blips out here, which correspond to our micro motion, all right? And so what we're now going to do is we're going to take advantage of that micro motion to kick ions out. And the way that we do that is, if you think of somebody who's on a swing set, and if you push them at the right time, you can kind of make them swing higher and higher, all right? But you kind of have to be pushing them at the frequency in which they're swinging. So we're just going to randomly say, this is the frequency of the micromotion in the y direction. All right, so they got this little wobble. So we can introduce yet another AC component, which is at the same frequency as their wobble, and each m over z will have its own little set frequency. We can start using that to push them further and further away from the center of the trap. And so once we push them enough, we can actually kick them out of the trap. Or if we push them just far enough, we give them enough motion in the trap to have collisions and fragment. And since each ion has its own frequency, basically what you can do then is you can sweep the secular frequency or this auxiliary frequency that you're just putting onto a single set of rods. So even though you have, we have our 4 rods, and they already have their AC components and DC components, you can now select any 2 and add yet another one, which is going to be another AC component, which has the same frequency as the secular motion of the ion that you're interested in. And so, let me go back here a little bit. So as you can see in this linear ion trap, the way they did this, see there's a slit in each of the rods. So the way these things are read out then is they will put the secular frequency in this dimension. So now the things are kind of trapped on the center. They pick the appropriate frequency. A particular M over Z gets excited and it gets kicked out of those slots. All right? We'll see how we detect it shortly. Or you can do the other thing. If you just want to isolate a particular M over Z in an ion trap, you can do just the opposite. You can apply all the frequencies except for the one of your ion of interest, then result as it kicks out everything but the ion that you hope to retain. And so the end result of all this is simply this, all right? So now what happens is our ions, various M over Z's are going to come in. We then scan that secular frequency in this dimension, and our ions start coming out as a function of M over Z, which we then basically record as a function of that frequency or time or whatever it is that you want. But this in the end gives us a mass spectra. Now the important part here is these ions, even though they're charged for the most part in this scenario, do not contain enough energy to detect easily. So a lot of times when you're working on an instrument, you're going to see somewhere that says there's a setting for a dynode voltage. And that's what these are right here. So these are usually around 15,000 volts. And so now what you're trying to do then, as the ions come out of the trap, you want to accelerate them into a high energy as you can and smash them into a surface. So now basically you're breaking them apart and trying to free their electrons. And so that is basically how we detect them. So like outside the trap, you're going to have incredibly high voltage here. Your ion's going to come up, they're going to smash into it. That's our conversion dynode. From there, all our electrodes go down into our electron multiplier. Now, before I go into this a bit more, you will often hear people mention mass analyzers. That's good. You'll also hear people mention mass detectors. That's bad, all right? Because it's just kind of like a nomenclature thing, but basically there are no mass detectors used in mass spectrometry unless you're some specific little research group. For the most part, all you can do is detect charge, all right? So in all these scenarios, we end up detecting charge. Like one of the few mass detectors you could think of would be like a nano oscillator or something like this, where you have a little thing which is vibrating, and then if mass gets added to it, its frequency of vibration changes. I would call that a mass detector. Everything else is a charge detector. And so the way this works, this is called a Venetian blind scenario or discrete dynode detector. And so each little dynode in this chain is set at a progressively higher voltage. And these surfaces are all coated with magic material, we'll say, where what you want to do then is that you have a high probability that every time a single electron collides with it, you get 2 or more electrons out. And so then what you're doing then is you're amplifying the number of electrons so that you can amplify your signal. And so then when it comes down here, basically what happens then, that's the signal you record. All these electrons kind of going onto a little collector at the end. And you once again equate that with time or some other setting of your ion trap, and it can give you a mass spectra. Now, multipliers come in all different shapes, forms, and sizes, depending on what you want to do with them. This is the Venetian blind, or like the discrete one I was just talking about. There's also many which are called continuous dynode detectors, and they operate on the same principle. The only difference is that instead of having discrete dynodes, they're made of a material, a lot of times glass actually, which is resistive, so you can put a large potential across it. And then what happens is every time an electron collides into the side of it, multiples are created, the field keeps getting higher, and they end up coming all the way down. And the reason these became so popular was simply because of time of flight. And so with time of flight, you need to have a very good timing resolution. And for the most part, back in the day, if you use these Venetian blind detectors, you can kind of think of it as every time, depending where an electron goes in, the total path before all the electrons get to the bottom is going to be different. The path length is going to be different. And so what happened then was these had horrible timing resolution. And so they switched to these, and these are probably still used a lot in time of flight instruments. So these are microchannel plates. So they're a continuous dynode type detector. So this is like one that would be used in a triple quad because they're not worried about timing. But what they did is they made them really, really tiny, like 10 microns in diameter, such that the path length variation was almost nil. And then what you do is you put hundreds of thousands of them together, and then you just collect it on a big plate on the backside. So then what happens is that you have a large area detector, and the timing of it, meaning the time from when the ions impact to when the electrons come out the backside, is going to be the same. So these were made very popular by time of flight. All right, and so I have, sorry about going along. We're just going to quickly cover one more mass analyzer using quadratic fields, and then we'll set everybody free. Sorry, I'm running a little bit long. All right, and so I saw Evan shake his head at me before when I was mentioning the static fields thing. So there are things called static traps, okay? And so this is where you're trying to use DC fields. And so one of the earliest ones was this Kingdon trap from 1920. And so you can kind of think of it as it's really almost just like a capacitor, a cylindrical capacitor. You have a wire running through the middle of a metal tube, and there's a voltage between these two. And what can happen then, if you get the conditions just right, you can kind of get things to zippity-doo-dah along these lines all day. The problem with this is, well, not the problem, but this sets up a logarithmic field, which isn't important right at the moment. But the problem with this is there's no real resonance which is usable here, meaning that there's not an M over Z factor that we can exploit to do an easy mass readout. So this is good at trapping, not so good at mass analyzing. So then, some years later, this Knight fellow came up with the bright idea. It's like, what if we try to modify the Kingdon trap and add a quadrupole field to it? And so we've just kind of spent all sorts of time talking about quadrupole fields and how we can exploit them to get an M over Z dependence in mass analyzer. And he said, okay, we're going to add it to this dimension, the Z dimension. And he was hoping to do that by, instead of just having a straight tube on the outside of the Kingdon trap, kind of have two cones at the end. And so this was good enough to approximate a quadratic field, but it didn't hit it precisely. And so with that drawback, and in addition to, he stayed with the standard technique of mass spectrometry, meaning that he tried to then use AC fields to eject particles, just like you would with an ion trap to get M over Z. This thing actually never worked too well. Then, lo and behold, some years later, machining got better. And so now what you do then is, instead of trying to approximate those fields, what if you actually could make the electrodes exactly as they should be to get those fields? And this is what we see here. And obviously, this will be what's known as the orbit trap, which is in use a lot today. And so the big advantages of this was it didn't just approximate the quadratic field. It actually made it through precise machining, which finally became available. And so I think the time frame on this, was like 1999. All right, and so this is what you want to do. You want to have a nice little company. You go back through the literature. You try to improve on something which shown that it could be a possibility. You make it work, and then have a big company come and buy you. And then you can retire. All right, so the way this works is everything in the reason this worked is two things. One, we'll get to it in a minute here, is that they were able to manufacture these rods. And two, they didn't eject the ions, but they detected them inductively. And so what that means is, okay, just like before, I said if we had a plus and a negative ion, they kind of attract one another. So now the same thing happens if you have a big conductor out here, a piece of metal, and you have a positive ion here. And you're now going to say connect this to ground or some infinite source of electrons. So what happens then is when this positively charged particle is here, an electron will come up and go here. It wants to stay balanced out. And so the way you do this detection then, you can kind of see like as long as there's a particle here, you're going to have this electron going this way. Remove the particle, this electron has no reason to stay here. It's going to go back out that way. And so now what you do then is you monitor the current through this little lead going to your conductor. In this case, which is the outside of the orbit trap. And you can see it split. I don't know if you can see this, but it is split. And so the reason for that is you kind of have, now think of it, I'll draw it simply. You have two halves, and you look at the current going on and off of both halves, but you subtract them. Boop. All right, so now if your ion first starts over here, it's positive. As it moves away, the field's going to want to come off here and go over here. And then as it comes back, that's going to keep changing. And the end result is you're going to end up generating a sine wave electronically. And since our quadrupole field is in this dimension, even though there is some m over z dependence in this direction and other things, the rate at which our ions oscillate this way is what's dependent on m over z. So what happens then is these things are oscillating, they're kind of generating their own little electric field, which forms out to be a sine wave. And so then you now introduce another, you have multiple different m over z's in there, they're each generating their own little frequency. Then you do the trick of doing a Fourier transform of that to find out all the various frequencies, which then give you your mass spectra. So I ran a little bit over time, but the point that I want to make out, or end with, is that you should now be able to make any of these mass spectrometers or understand how they work, okay? Everything we covered is in all of these. And so what people do is just make different arrangements and combinations of them. And they have their pluses and minuses and different utilities, and some work better for other things, and it's kind of up to you as to what you want to use. But anyways, hopefully you'll go out and check out some of the demos. I will be over at a table which has a bunch of mass spectrometer spare parts, and such as orbit traps, quadrupoles, things like this. And then you can see like how they're shaped. And the reason they all have these funky shapes is just to make that all-important quadratic field. So thank you guys for sitting through that. I appreciate it. And hopefully I didn't bore you too much. Thank you.